Until now, we've deployed applications and exposed them through services. But real applications need configuration. They need database passwords, API keys, authentication tokens, and other sensitive values. Storing those values directly inside application code is a bad practice. Kubernetes provides secrets to manage sensitive information securely and environment variables to make those values available inside containers. Today we'll learn both concepts and then build a working example. Imagine a developer writes a password directly inside the application code. Everything works fine at first, but then the code is pushed to GitHub, shared with teammates, or exposed accidentally. Now the password is visible to everyone. This is one of the most common security mistakes in software development. Instead of hard-coding credentials, we should separate application code from sensitive configuration. A Kubernetes secret is an object designed to store sensitive information. Examples include passwords, API keys, access tokens, and certificates. Instead of embedding these values inside the application, Kubernetes stores them separately and allows pods to consume them when needed. This creates a cleaner and more secure deployment model. At first glance, config maps and secrets look very similar. Both store key value pairs. The difference is their purpose. Config maps are used for regular application configuration. Secrets are used for sensitive information. A good rule of thumb is simple. If you wouldn't post the value publicly, it probably belongs in a secret. One important thing to understand is base 64. Many beginners think base 64 means encryption. It does not. Base 64 is only an encoding format. Kubernetes stores secret values encoded as base 64 strings. Anyone with access to the encoded value can easily decode it. That's why base 64 helps with data formatting, but it is not a security mechanism by itself. Creating a secret is only the first step. Applications need access to that information. The most common method is using environment variables. Kubernetes reads the secret and injects its value into the container when the pod starts. The application can then access the value as if it were a normal environment variable. In this lab, we'll create a secret, inspect its contents, understand how base 64 works, inject the secret into a pod, and finally verify that our application can access the value through an environment variable. Let's switch to the terminal and build it step by step. Before we jump into the terminal, let's look at what we're building. First, we'll create a Kubernetes secret containing a database password. Then, we'll deploy a MySQL database pod. Instead of hard-coding the password, MySQL will read it directly from the secret. Next, we'll deploy a Backend Pod that also consumes the same secret. Both applications will use the same credential without exposing the password in their YAML files. To allow communication between them, we'll create a Kubernetes service called MySQL-Service. The Backend Pod won't need to know the database IP address. It will simply connect using the service name. By the end of this lab, we'll have a small but realistic architecture that demonstrates how secrets are used in real Kubernetes environments. Let's start by creating a dedicated project folder for this lab. As with the previous episodes, all the Kubernetes manifests used in this demonstration are available in our GitHub repository, so you can download them, follow along, and experiment on your own environment. I'll leave the repository link in the video description. Here I'm creating a folder called secrets-demo and moving into it. Inside this directory, we'll store all the YAML files for our secret, database pod, service, and backend pod. This is also a good practice in real projects because keeping Kubernetes manifests organized makes them easier to maintain and version using Git. Before creating the secret, we need to understand one important concept. Kubernetes stores values inside the data section using base 64 encoding. That means our password must be converted into a base 64 string before we place it in the secret manifest. Remember, base 64 is not encryption. It simply transforms data into a text format that Kubernetes can store and process consistently. Let's encode a password and see what happens. Notice that the original password has been transformed into a different string. This is the value Kubernetes expects inside the secret definition. In a moment, we'll use this exact value inside our YAML manifest. Now let's create our first Kubernetes secret. In this example, we're creating a secret called DB secret. Inside the data section, we're storing a value named MySQL password. Notice that the password is not stored as plain text. Instead, we're using the base 64 value we generated a moment ago. Another important field here is the type. The most common secret type is opaque, which simply means we're storing custom key value pairs such as passwords, API keys, or tokens. Let's apply it to the cluster and verify that Kubernetes creates it successfully. Perfect. Kubernetes has successfully created our secret. We can see the name of the secret, its type, and the number of values it contains. Notice that Kubernetes does not display the actual password. This is intentional. Even when listing secrets, Kubernetes avoids exposing sensitive information directly on the screen. At this point, the secret is already stored inside the cluster and ready to be consumed by applications. Let's inspect it a little further and see how Kubernetes is actually storing the value internally. Now we're looking at the actual secret stored inside Kubernetes. Notice that our password is not displayed as plain text. Instead, Kubernetes stores it as the base 64 value we generated earlier. If we focus on the data section, we can see the key name MySQL password and its encoded value. This is where many beginners get confused and assume the password is encrypted. But remember, base 64 is only encoding. Anyone with access to this value can decode it back to the original password. Let's prove that right now. If base 64 is only an encoding format, we should be able to recover the original password in just a single command. Creating a secret is useful, but by itself, it doesn't do much. The real power comes when applications consume those values. Let's build a small example with two pods. A MySQL database pod will use the secret as its root password. A Backend Pod will use the exact same secret as a database credential. This is a very common pattern in real Kubernetes environments. Let's take a closer look at what's happening here. On the right side, we have our secret called DB-secret. Inside it, Kubernetes stores a value named MySQL password. On the left side, we have our MySQL pod. Notice this section under env. Instead of writing the password directly, we're using value from and secret key ref. This tells Kubernetes, go find a secret named DB secret and retrieve the key. When the container starts, Kubernetes reads the secret and automatically injects that value into an environment variable called MySQL root password inside the MySQL container. So the connection between the pod and the secret happens through this secret key ref configuration. The password never appears directly inside the pod manifest, but the application can still access it at runtime. Let's apply the MySQL configuration pod. Perfect. Our MySQL pod is now running. What happened behind the scenes is that Kubernetes created the container, read the secret we created earlier, and injected the password into the environment variable expected by MySQL. From the application's perspective, it simply receives a normal environment variable. The application doesn't know where the value came from. It only knows that the variable exists when the container starts. This confirms that Kubernetes successfully injected the secret into the container. Notice that we never wrote the password directly inside the pod manifest. The secret remains separate while the application receives the value it needs at runtime. This separation is one of the key security practices when working with Kubernetes. Now that our database is consuming the secret correctly, let's create a service so other applications can discover and communicate with the database using a stable network address. At this point, our database is running, but there's still a problem. Pods are temporary in Kubernetes. If this pod is recreated, its IP address may change. Applications should never connect directly to pod IPs. Instead, Kubernetes provides services which give applications a stable network endpoint. Let's create a service that will expose our MySQL pod inside the cluster. Now, if you've watched episode 6 on services and networking, this configuration should look familiar. For those who need a quick refresher, Here's what's happening. On the right, we have our MySQL pod with the label app equals MySQL. On the left, we have a service called MySQL-service. The service uses a selector to look for pods with the label app equals MySQL. Because our MySQL pod has that label, Kubernetes automatically associates the service with the pod. From that point on, applications don't need to know the pod IP address. They simply connect to MySQL service, and Kubernetes takes care of routing the traffic to the correct pod. This becomes extremely important because pods are temporary and their IP addresses can change, while the service provides a stable endpoint for communication. Now that our database has a stable network identity inside the cluster, let's create a backend pod that will consume the same secret and communicate with the database through this service. For this demonstration, we're using a simple BusyBox container. The goal isn't to run a real application yet. The goal is to demonstrate how a backend can consume a secret and communicate with another service inside the cluster. Before we continue, let's take a moment to understand this command, because you'll use it constantly when troubleshooting Kubernetes applications. Let's break it down. The kubectl exec command allows us to execute commands inside a running container. Think of it as opening a terminal session directly inside the application. This is the name of the pod we want to access. The -i keeps the session interactive, and the -t allocates a terminal, giving us a shell experience similar to logging into a Linux server. Finally, esh is the shell we want to start inside the container. Some images have bash, others only have sh. BusyBox uses sh. Now we're inside the container. Any command we run from this prompt is executed inside the backend pod, not on my local machine. Notice that we're now operating inside the container itself. This is extremely useful for debugging applications, checking environment variables, testing connectivity, and inspecting files. Now let's verify whether Kubernetes successfully injected our secret into this container. Perfect. The application can now access the database password through a normal environment variable without storing the credential directly in its code or manifest. Now let's verify that our backend can discover the database using the Kubernetes service we created earlier. This is exactly what we wanted to see. Kubernetes DNS successfully resolved the service name and returned the cluster IP assigned to our database service. Notice that Kubernetes expanded the short name MySQL-service into the fully qualified DNS name mysql-service.default.svc.cluster.local. This is the internal DNS naming convention used inside Kubernetes clusters. The NX domain messages are generated because BusyBox tries several DNS search paths while resolving names. What's important is that Kubernetes eventually found the service and returned its cluster IP. So despite those messages, name resolution was successful. Let's recap everything we built. First, we created a secret to store a database password. Then, we deployed a MySQL pod that consumes that secret as its root password. Next, we deployed a backend pod that consumes the same secret as a database credential. Finally, we created a service that provides a stable network identity for the database. The backend can now discover the database using the service name, while Kubernetes handles the networking behind the scenes. This combination of secrets, environment variables, and services is a very common pattern in real Kubernetes applications. Today we learned how Kubernetes stores sensitive information using secrets, how applications consume those values through environment variables, and how services allow workloads to communicate reliably inside the cluster. In the next episode, we'll explore volumes and persistent storage and learn how Kubernetes keeps data alive even when pods are recreated. See you in the next episode, and thanks for watching.